All right, today's lecture is going to be on VSEPR, or three-dimensional structures. What is the geometric shape around the centralized atom in a molecule? Now, when we just got done doing Lewis structures, and a Lewis structure is a 2D structure, and it shows how the atoms are bonded and who's bonded to who. It shows the bonding arrangement, but it really doesn't give us any other indication about the true molecular shape of the molecule. That's where VSEPR comes in. Now, VSEPR, again, it's an acronym, it's a theory that stands for valence shell electron repulsion. The electrons in the bonds and the lone pairs, they repel each other. So VSEPR says, let's get these electron areas as far away from each other as possible, utilizing all three dimensions of space. And that bonding arrangement and spacing will result in a specific geometric shape. And a lot of these shape names you've already heard before, and there's a few more that we'll add on the next couple pages in your packet. Now, one other vocabulary term that's kind of new is called an electron domain. An electron domain is an area of where electrons are located, either as bonds or as lone pairs of electrons. An electron domain not only can be a bond, but it can also be a location where there's a lone pair. And again, we're specifically looking at the central atom. So down below, I've shown two examples of molecules with a Lewis structure. The first one here, element X is the central atom. Elements Y, both Y and Y there, those would be what's called terminal atoms, atoms coming off of the central atom. The terminal atoms are only bonded to one atom, X. They do not have a geometric shape around them because they're bonded to only one other element. Okay, in accordance to Y, X is always 180 degrees from it. Okay, it's in a straight line. But element X, the central atom, because it's bonded to more than one thing, it will have a specific VSEPR shape to it. Now, how many electron domains does element X have? So I'll create a little column here. And element X has 3 electron domains. It has a single bond, a double bond. Now, misconception, some students think that because there's a double bond there, it counts for more than one. It doesn't. A double bond or even a triple bond counts as just one electron domain. Each bond is its own electron domain, no matter if it's a single, double, or triple. Lastly, there's also an electron domain for the lone pair of electrons in element X. Therefore, there are 3 electron domains. Now, what VSEPR says, those 3 areas of electron densities must be as far away from each other as possible. Now, if you can think back to honors chemistry, what bond angle results with the greatest bond separation? And for those of you that said 120 degrees, you're correct. So 120 degrees from the lone pair, the first electron domain would be the bond. Okay, then another 120 degrees from that would be the next bond. And then 120 degrees back to the top. This geometric shape, then look, electron domains, whenever we have 3 electron domains, the areas of those 3 electron densities are always going to be separated by 120. This geometric shape is said to be, okay, trigonal or trigonal planar. Trigonal planar is a 120 degree bond angle, okay, which results whenever we have 3 electron domains. Now, those electron domains, they could all be single bonds. It could be 3 single bonds. It could be all double bonds. It could be, a lone pair and then 2 bonds that we have here. Not too many other possibilities there for trigonal planar geometry. But what that means is the 3 areas of electron density must be 120 degrees from each other. Okay? Now, the name of this shape is not trigonal planar. Trigonal planar would be named if we have 3 bonds coming off. Because there's a lone pair, we cover up the lone pair and we look at the shape that results. The lone pair is not in accordance with naming. So even though this is trigonal planar geometry, the actual geometric name of this molecule, if I cover up the lone pair, we get a molecule that looks like a bent V. And what do we call that geometric shape? Bent. So even though this is trigonal planar geometry, the actual molecular shape of the molecule could be said to be bent because we only look at the atoms that are bonded off of element X, and we see it's a V pattern, which would be a bent molecule. Okay, so the 120-degree bond angle is what comes from the number of electron domains and how as far apart as we can get them. Whenever we get to molecules that have more than 4 areas of electron density, here's a situation where we have 5 electron domains. Because we have more than 4, this is a hypervalent molecule, which means it does not follow the octet rule. Because it doesn't follow the octet rule, the Lewis structure for it is pretty hunky. It's hard to do it because of the fact that with true Lewis structures up at the top, we want to keep them at the 90-degree bond angles. But when we have 5 or more bonds, the Lewis structure really is hard to do. We just kind of just throw it and make it almost look like a star. But when we do the VSEPR structure of that, if you can remember back, when we have 5, the interesting thing is 3 of them go into the disk of material much like up above with the trigonal planar. So 3 of the bonds creates a disk of material which is 360 degrees in one plane all the way around. So each of these bond angles is 120, 120, 120, or 360 degrees all the way around. So 3 electron domains forms a 120-degree bond angle. And then if we think of that and make that disk a flat disk, we put one more at top and one more at the bottom, which ends up being then a 90-degree to the disk. So whenever we have 5 electron domains, we have bond angles of both 120 degrees and 90 degrees. It's the only number of electron domains that we actually have more than one bond angle. Okay? So 120 degrees and 90. And that does cause us to have a little bit different in geometric shapes, which I'll come back and talk about in a few minutes here. Okay, so when we have 5 electron domains, we're going to have 3 in the disk, and then 1 above the disk and 1 below the disk, making a 90 degree to the other 3 that form 120 degrees all the way around. Okay. Now, the name of that shape is said to be trigonal bipyramidal. Okay, trigonal bipyramidal. In essence, we're forming 2 pyramids, 2 triangular pyramids. So if I go ahead and map this structure out on the top, you will see that there is one pyramid at the top, a triangular base pyramid. So it's got 3 angles coming down to form a triangle at the base, and then another one on the bottom. So we get 2 pyramids, in essence, base to base, forming almost this diamond pattern. That's trigonal bipyramidal shape. Okay, so after you draw the Lewis structure, figure out how many electron domains you have, and then you can go through and create the geometric shape. Okay? And again, lone pairs count for electron domain just like a single bond and a double bond as well. So let's go ahead and review the basic shapes you need to know. So in the next couple pages, I'm going to go over the names of the shapes that you need to know for the national exam. So let's turn the page. Oops. So on your packet, okay, I've given you this page, which is a very important page to look at. The number of electron domains. If it's a central atom, you must have at least 2 atoms coming off of something in order for it to have a geometric shape. What is the geometry shape around element X? If you have a diatomic molecule where it's only bonded to 2 atoms bonded together, there is no central atom. If there's no central atom, we don't have to worry about a geometric shape. If I have 2 atoms bonded to each other, they can only form a bond which is 180 degrees apart from each other. There is nothing else that can happen with that. So to have a true centralized atom in these geometric shapes, you must have an atom that has at least 2 atoms bonded off of it. All right? So if you have 2 atoms coming off of it, you have 2 electron domains. This will always be a linear geometry. The bond angle that separates the 2 adjacent atoms, or the 2 terminal atoms, they are separated by 180 degrees. And that's why we call it a linear geometry. This hybridization, I'll come back and talk to it at another later lecture. This will be long enough. If we have 3 electron domains, like we already saw on the previous page, we're going to get a trigonal planar geometric shape, and we'll have 3 areas of electron densities, and they will form 120 degrees, as I said before. If we get up to 4 electron domains, now we're going to form a tetrahedral structure with a bond angle of 109.5 degrees. A great example of that is the molecule methane. If you remember back to Honors Chem, we did that dash and wedge method to show the three-dimensional shape. Hard to do in 2D paper. But all of these hydrogens to hydrogens, all of those are 109.5 degrees. Now, if you can't remember 109.5 degrees, believe it or not, in the national exam, they give you credit for anything that is typically around between 105 to 115 degrees. So as long as you're in between there, I tell students if nothing else, put down 110. But if you can remember 109.5, great. If not, they do give you a little bit of wiggle room. So think of 110 if you have to. 5 electron domains, I said this is the odd one in the fact that you can see here in the disk, they form 120 degrees. 3 of them do. And the other 2 electron domains go top and bottom to the disk. Okay, we got that disk, top, and bottom. And we get the different bond angles. And lastly, the most amount of electron domains you can have is 6. With that structure, we have, in essence, the disk of material separated into 4 chunks, or all of them are 90 degrees. So in essence, we've got like a piece of paper. And then we have one coming right off the top and one coming right off the bottom. So every bond angle in that measurement is 90 degrees. Okay, in essence, we're forming almost like an Egyptian pyramid, which is a rectangular or square pyramid base shaped. Another one on the bottom, where we're having 2 square pyramids on top of each other, 90 degrees. Okay? All right, so let's turn the page and look at all the geometric shape names that you need to know. All right, so if we have 2 electron domains, okay, you're going to have non-bonding domains would be lone pairs of electrons. They like to use the terminology on the national exam as non-bonding electron pairs. So lone pairs of electrons or non-bonding electron pairs. Whenever we have a centralized atom with 2 electron domains, not one of those electron domains cannot be a lone pair. For example, if it bonded to Y and this guy had lone pairs, this would still be a diatomic molecule. There is no central atom. We can't count these lone pairs as if they are a terminal atom. To truly have a linear shape and have 2 electron domains, whenever we have 2, none of those electron domains can be a non-bonding or a lone pair. It has to be bonded to 2 atoms. Okay? So a great example of that would be carbon dioxide. So they give you an example of that where, again, we have 2 double bonds. The lone pairs on the oxygen is not important because we're looking at the geometry around the carbon atom. The carbon atom has got 2 bonds. Now, I know they're both double bonds, but we don't treat them differently. It has 2 electron domains because each electron domain is a double bond, and therefore this would be a classic example of 2 electron domains where the carbon is bonded to only 2 atoms. It has no lone pairs around it, and therefore it has a linear geometry. If you have 3 electron domains, there's 2 possibilities. The first is when we have 3O, where we have 3 atoms coming off of an element. Whenever we have that situation, we say it is trigonoplanar. Okay? An example of that would be BH3, where it's bonded to 3 atoms, no lone pairs. That's a trigonoplanar shape. We can also get 3 electron domains when we have 2 atoms and a lone pair, which I showed you in the previous page. Here's an example of that. Hard for me to see what molecule it is. Looks like it's nitrogen dioxide. Or I should say not nitrite. Looks like it's the nitrite ion. Okay, the nitrite polyatomic ion. There we can see the shape where we have a double bond, a single bond, and a lone pair. Now, we don't call it trigonoplanar. Trigonoplanar is only when it's got 3 atoms coming off of it and no lone pairs. Because one of the electron domains is a lone pair, we cover that up. What we're left with is a geometric shape of a bent V. So we call this bent. So bent means that it's got one of the electron domains as a lone pair. 3O, it does not. It's all bonds. All right, then we go up to 4 electron domains. When we have 4 electron domains, there's 3 possible sequences. 4O, where all of the electron domains are a bond. And again, we talked about methane already. This is methane, where we see the true tetrahedral geometry. We call it tetrahedral when it's got 4 bonds coming off the central atom. Then we can have 3-1. 3-1 is where one of the areas is a lone pair and the other 3 areas are bonded atoms. A great example of that is NH3 ammonia. And again, all of these bond angles are 109.5 degrees. Okay, but we don't call it tetrahedral because tetrahedral is only assumed when it's 4 bonds, where all of the electron domains are bonds. In this case, one of the electron domains is a lone pair. So when we cover up, if you take your finger right now, the thumb, and cover up my lone pair, what I'm left with is literally almost a triangular base pyramid. And that's why we call it trigonal pyramidal. Whenever we have 1 lone pair and 3 bonds coming off of a central atom, that's trigonal pyramidal. The last one is 2-2, where 2 of them are lone pairs and 2 of them are bonded atoms. Great example of that is the molecule water, where we have now 2 of those areas are lone pairs. And then we have 2 of the areas are bonds. So again, if I take my thumb and cover up my lone pairs, what I'm left with is literally a bent V, in which the 2 Y's are separated by 109.5 degrees. Again, we call that shape bent. So we have 2 different situations of bent, a 2-1 and a 2-2. So whenever we have 2 atoms coming off the central atom, and there's any number of lone pairs, it will always be a bent structure. Okay, let's turn the page to the last. All right, now the last page here, when we have 5 and 6 electron domains, this is when we will have a hypervalent molecule, which means we are going to go over the octet rule. And again, to go over the octet rule, the central atom is going to be a non-metal in periods 3, 4, 5 on the periodic table. So any element to the right of the staircase in periods 3, 4, and 5. Okay, typically. 6 and 7 possibly, but usually they're 3, 4, or 5. Now last year we only talked about 2 names in which you have 5O, where all of the areas of electron domains are bonds, a 5O. Classic example is PCl5, which we see here to the right, where we have phosphorus in the middle and there's 5 single bonds to 5 chlorines. There are 10 electrons around the central X atom, the phosphorus in this case. It's hypervalent, but because phosphorus is in periods 3, it is big enough that it can have enough size that it can separate those electron domains to 109.5 degrees. All right, so with that, the geometric name for that shape is trigonal bipyramidal. Down below, when we have 6 octahedral, again, now we have, instead of 3 in the disk, we have 4 bonded atoms. In essence, it's like a piece of paper. And then we have one coming right off the top of the paper and one coming right below the paper. Again, no matter how we look at these bonds, they're all 90 degrees, and that's octahedral. Great example of that would be SF6, sulfur hexafluoride. Okay, where again, sulfur's in the middle, and now there's 6, it's bonded to 6 fluorines with single bonds in all the locations, octahedral. Now we have a couple of new names that come about these geometric shapes. What are they? All right, so the first one would be where we would have 4 bonds coming off the central atom and 1 lone pair, 4-1. The classic example of that is sulfur tetrafluoride. Sulfur tetrafluoride is the classic 4-1 compound, and I think it's the only one that I know of that's ever been in the national exam. When I get done drawing sulfur hexafluoride, we end up getting or having one lone pair and 4 atoms. So when we have this molecule, the question becomes, where does the lone pair go? And what they've found out through a study is that the lone pairs actually repel more than electrons and bonds. And therefore, the lone pairs have to go in the disk of the material. They cannot go on the bonding angles that create 90 degrees, the top and bottom. So when we draw this molecule in three-dimensional shape, the lone pair will go off into one of the sides. All of the other atoms will go in the other locations. This geometric name is called seesaw. Oops, S-E-E, my bad, seesaw. Why a seesaw? Well, if I actually take this molecule and I rotate it 90 degrees, it literally looks like a seesaw. Here is the base where the seesaw sits. The F's are here, and you think of a couple kids riding the seesaw, it can go back and forth. So the name of this shape is seesaw. So whenever we have five electron domains and one of them is a lone pair, the name of that geometric shape is seesaw. Next possibility is 3, 2. Again, when we add these all up, you'll notice they always add up to 5. So therefore, we're going to always place these electron domains. It's going to have 5 electron domains, and therefore it's going to go in this 120, 90 degrees. Now you'll notice that 2 of the electron domains are coming from lone pairs, and they go in the disk of the material. And what I'm left with, as you can see here, is a shape of the other atoms form a T. They literally form a 90 degree T shape, and that's what it's called, T shape. So whenever you have a 3, 2 geometric sequence, again 5 electron domains, where 3 of them are bonds and 2 of them are lone pairs, you're going to get what's called T-shaped. Again, another new name. Lastly, we can get 2, 3, where 2 of them are bonded to atoms, and then there's 3 lone pairs. And because all 3 of the lone pairs goes in the disk, you'll notice that we have 2 terminal atoms, and because of the disk, all 3 of them are lone pairs. What we're left with is the terminal atoms being separated by 180 degrees. So again, it now comes back to a shape you're very familiar with, linear. So these geometric shape names, it really comes down, you might want to make some flashcards, but just go through the basic shapes, make one of each, and just rip through them a couple times going to the national exam. It's a very quick question, easy question, but one that you just got to be aware of and be able to do quickly, naming these shapes. And it comes down to just practice. That's why you need to do those homework pages on the next set of pages where you have those 3 pages of lots and lots of examples to go through. Last couple examples in octahedral is 5, 1 and 4, 2. Now, because they're all equal degrees, it doesn't matter where they go. So usually we put the lone pair on the top or bottom. And what we get now is, if we look at the shape of it, it forms literally like an Egyptian pyramid. It forms a square-based pyramid, so we call it square pyramidal. Again, I always cover up the lone pair. Take your thumb, cover the lone pair. What are we left with? We're left with all the other atoms form a square-based pyramid, square pyramidal. And for 2, the only requirement with this is the lone pairs must be opposite each other, and therefore the last 4 electron domains are bonds, and they are going to form literally a piece of paper. And because it's 2-dimensional, we call it square planar. Because planar means it's all exists in one plane, it's a flat, it's like a sheet of paper, where at each of the corners of the piece of paper, there is an atom. So therefore all the bond angles are 90 degrees, and it's a flat square shape, square planar. So most of the names we learned back in honors chemistry, but the other names are ones that you can easily look up and go on the sheet. So the last page here in the packet, I've shown you all the geometric names and their shapes and their bond angles. This just kind of goes through what I just covered. So I want you to be aware of it. It's not difficult. It's just a matter of you putting enough time to practice and knowing the name of the shape. Now, one last thing. Sometimes they ask you to justify a geometric shape or bond angle. As an example of that, let's say we have a chemical formula let's say with this molecule right here. And they say in the national exam, a student hypothesizes that the bond angle formed between the H and the O is 90 degrees. Is that student correct? Obviously the answer is no. Students want to think that it's right, but it's not, because you have to think of VSEPR. VSEPR says what's the farthest bond angle we can get. Now if I look at this bond angle, it's not 90 degrees because that's the Lewis structure. In real life, how many electron domains does this molecule have? Hopefully you said 3. So if you're asked to justify the bond angle or the geometric shape of this, you would say this chemical compound has 3 electron domains. Okay, dot, 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 remember, 3 dots, therefore, the bond angle is 120 degrees, okay? Or the geometric shape is trigonoplanar, not tetrahedral. Okay, why? Because 120 degrees is the maximum separation of 3 electron domains to minimize the electron repulsion. What VSEPR really means, guys, and this is the key thing to put down, is that 120 degrees or a trigonoplanar shape results whenever we have 3 electron domains. Why? Because 120 degrees is the farthest we can get those 3 areas of electrons, those 3 electron domains. 120 degrees is the maximum separation utilizing all 3 dimensions, and that will minimize the electron repulsion. And the minimum electron repulsion will create the most stable geometric shape. That's how we justify a bond angle or shape. So again, it's an FRQ question. So if they ask you to justify that bond angle or shape, along with saying what the correct bond angle or shape name is, the harder part of that then is to explain it. And again, this is something you have to just get down. You have to say that this bond angle creates the maximum separation of the electron domains, and that minimizes electron repulsion, creating that geometric shape or bond angle. All right? Good luck. Go through the homework. If you have questions, again, please send me an email or shoot that out. But again, please try to, the homework literally, unless you don't have the names down, which you might not, should not take you very long, because you're just filling in the next column that says geometric shape name. All right? Good luck.